take a moment to thoroughly read the question prompt. Here we have a system where we have two blocks. We have one block M1. We're given the mass of that block. We're told that it's on a rough horizontal surface. That tells us that we're going to have to include friction. And this block is connected via a rope and pulley system to another block M2. So we can see here this block is on a horizontal surface. If it were just by itself, it would want to stay put. It has a rope connecting it to another block. This block is on an incline. This cart will tend to roll down. It will tend to pull the block to the side. In this particular case, we want to know what is the maximum mass of M2 for which the system will remain motionless. In this case, if we are remaining motionless, this tells us that the velocity should be 0 and that the acceleration should be 0. If we want to know about the mass of cart 2, and we're talking about velocity and acceleration, mass is causes motion because of the weight, the gravitational force, and so we should approach this using forces. The first thing that we'll do is to draw free body diagrams. Since we have two different objects, we're going to have two different free body diagrams, one for each. Let's start with block 1. The first thing that we'll do is draw a circle around the object to identify points of contact. I have a point of contact here that's with a surface, and whenever I have a surface, I know that I have a normal force, and I also have a friction force. I have a point of contact here that's a rope. A rope carries tension. Those are all my points of contact. We also have the weight of the object, and I'll call that W1 for block 1. We'll do the same thing for the other block. I'll draw a circle around it, identify points of contact. Here I'm in contact with a surface, so I have a normal force. I'll call this N2 to distinguish that, and I'll go back and call the other N1. Oftentimes I would have friction, but here I have a cart on rollers, so we're going to assume that friction will be 0 in this case. I also have a rope there, so I'm going to have a tension. And then finally I'll have a weight. W2 for the weight of block 2. Now that I've identified all the forces, I'm going to put these in a free body diagram. I'll start for block 1. Block 1 should be moving across a horizontal surface, so I'm going to draw my free body diagram with horizontal and vertical axes. For block 1, I have a tension. That tension pulls in the direction of the rope. I have a weight that is going to pull downwards. I have a normal force that's going to pull upwards. And I have a force of friction. In this case here, I've drawn all of them the same size around the particle in the center. I've drawn them all the same size because we said that the acceleration would be 0. So my acceleration will be 0 and my velocity will also be 0. All of this is for block M1. I'll do the same thing for block M2 now. Now M2 is on a inclined surface, so I'm going to incline my axes as well. The X and Y axes should still be perpendicular to one another, but they're going to be inclined at a 40-degree angle to match the incline of the ramp. Notice the 40 degrees here, and so the 40 degrees there. Now I can look at the forces on cart 2. I have tension. That tension always acts towards the center of the rope, along the rope. So that tension is going to act here. I have a weight. The weight always acts straight down, because the Earth doesn't care whether you're on an incline or not. It's going to pull everything straight down. I have a normal force here that needs to be normal to, perpendicular to the surface that it's on. And then I'll put a particle at the center that all of these forces are acting on. Same as before, the acceleration equals 0. In this case, when I have multiple forces that are in all different directions, it's a little bit more difficult to make them so that the net force is 0, but we want to try to make them more or less balanced. But I've accounted for all of the forces, and I have my acceleration and velocity vectors. The last thing that I need to do is to identify any action-reaction pairs of forces. In this case, because we're assuming a massless string, we can say that the two tensions should be the same as each other, because just one rope connecting the two. We have our free body diagrams. The whole point of our free body diagrams is to use them to employ Newton's second law. Newton's second law says that force is mass times acceleration. This is the net external force. In practice, what Newton's second law says is that the sum of the forces acting in the x direction should be the mass times acceleration in the x direction. The sum of the forces acting in the y direction is the mass times the acceleration in the y direction. And this is why it was important for us to line up our axes to match the accelerations of the objects. So now I'm going to have two equations for the first object and two equations for the second object. Looking at the first one here, I have tension that is acting to the right, so it's positive. I have static friction is acting to the left, so that's negative. Make sure you include the subscript for the mass that you're considering. In the y direction, I have normal force acting up. I have weight acting down. For object number 2, I have to break up one of my forces into components. My weight here has a component in the y direction and a component in the x direction. This should still be 40 degrees there. So for block 2, the cart, I have an x component of the weight in the positive x direction, kind of down and to the right. I have the tension acting up and to the left. And then in the y direction, I have the normal force acting up. I have the weight acting down. And then the assumption that we had in this case was that the acceleration should be 0. And so in fact, all of these terms are going to be 0 if we're assuming that these aren't moving. So we can kind of see where we need to go here. We want the maximum mass of M2. The maximum mass of M2 is going to give us the maximum tension. That tension is going to pull back on block 1, and block 1 has to be held in place by its friction. And so the maximum value of block 2 is going to correspond with the maximum value of the friction. So what we're going to do now is rewrite all of these equations, plugging in what we have for each equation. This is assuming a maximum static friction, which is going to coincide with a maximum weight of block 2. In this case, we can get rid of weight and we can start writing things in terms of their values. The x component of the weight of block 2 is this portion right here. This is the x component. The full value of the weight is mg, just like it is for block 1. This side is opposite that 40-degree angle, and so it's going to be m2g now is the value of the weight, and then the sine of the 40 degrees there is going to give us the x component. And then if we look at the y direction, we'll get the cosine there. because you'll see that the y component of the weight is adjacent to that 40-degree angle there. But actually you'll see as well that we don't need the normal force for the cart. There's no friction there, and so the normal force isn't really going to affect us. But what we're looking for here is the maximum weight, maximum mass of block 2, which is going to be related to the tension, and the tension is related to the maximum value of the static friction. And so I can say a couple things from here. I can find the normal force for block 1. I can take this quantity now and plug that in there. This is the maximum value of the tension that we can have. That can be balanced out by the static friction. Now I can rewrite this, and I can say that this maximum value of the tension is equal to the frictional force. And now I can take this right here, and I can plug that in over here. In this case, I know all these values. I found the maximum tension that I could have based on the maximum static friction. The maximum tension is going to correspond with the maximum weight of block 2. The maximum weight of block 2 relates to the maximum mass of block 2. So now I have all those values. All I need to do is plug them in. I've plugged all these values in. I see that I've got a value of G that I can just cancel out. And now all I have to do is plug this into my calculator to solve for M2. Here I found that M2 is 1.789. That should be in kilograms if we're measuring a mass. And then notice how I have 2 sig figs and 2 sig figs, 2 sig figs everywhere else. So if I round this to 2 sig figs, I will get 1.8 kilograms would be the maximum value of M2, for which static friction can hold this block in place. If M2 gets too big, it will pull too hard on that rope, it will break M1 free, and the whole thing will start moving. We'll see that in the next example.